Swayam Prabha. Digital India. Educated India.
Welcome to module 41. Today we shall take up three more interesting properties. First, countability, second, countability, and separability. Once again, we go back to metric spaces for motivation, especially the Euclidean space itself. So these properties, just like path connectivity, compactness, Lindelof, etc., they can be classified as smallness properties, but not exactly. We have given a formal definition, and this first countability and second countability does not fall into that, though separability does. Now, why combining them? But they are quite going hand in hand. That's why I recommend. But nevertheless, there is some vague feeling that these conditions put some restriction on the size of the topology. You shall see why. Okay, and it's better to leave it like that instead of getting into formal definitions. So what are we going to observe here? First, let me take any metric space. Okay. The base for a metric space topology is you take the balls of radius positive at all the points, right? Suppose you are fixing one point and then looking at all the neighborhoods of that point. Then, instead of taking all the balls of positive radius, you can simply restrict yourselves to balls of radius 1 by n. Balls of radius 1, 1 by 2, 1 by 3, 1 by 4, and so on. To wherever the discussion of neighborhoods is involved, only these balls will be sufficient. So this idea leads to the notion of first countability. With the usual topology on R, we know that the set of rational numbers is countable as well as dense subset. The same thing is true for all Euclidean spaces also. Only thing you have to do is you take all points such that all the coordinates are rational. That's also a countable set, and it will be dense inside Rn. Okay, so this gives you another notion which is called separability. Okay, before going to the third one, let me state a theorem here for metric spaces. And then that will induce the second definition. Okay, the third definition. Start with any metric space with a countable dense subset A, just like Rn. But now I am generalizing it. For any n, for any metric space, all that I want is a countable dense subset, similar to Q or points with rational coordinates and so on. Okay. with this much of hypothesis, I want to conclude the following thing. Then there exists a countable base for the topology X. Okay, D is a metric space, so D is a metric, and the topology X tau D has the property that it has a countable base. In particular, all Euclidean spaces have countable base. So what does it mean? It means that every open subset is arbitrary union, but the members coming from a fixed countable set. That is the beauty. So that already puts a lot of restricted condition on the topology. It doesn't say, remember, it doesn't say that number of open sets is countable. No, because you are taking arbitrary union. But now all the open subsets are unions of members from a one single family of countable sets. So that is a countable base. Okay, so that's quite strong condition. So how to prove this one? It's a one-line proof. Put B equal to collection of all balls of radius 1 by n, not at all the points, but only at the points of A, where A is a countable dense set. So A is inside, little a is inside A, n is inside a natural number. Okay, this is clearly a countable collection, because A is a countable set and n is also a countable set. So there are two different variables here, but n cross n is a countable set. This collection B is a base for a topology that it satisfies B1 and B2. This does not need any extra, hypothesis. I know this kind of things you have done, so you must do that one. Okay, that they form a base. It means what? Once you take finite intersection of two of them, and a point there, show that there is a smaller one contained inside that at the point, and so on. That kind of B1 and B2 you have to verify. So this I will leave it as an exercise. All these are open subsets in tau D, right? Therefore, B, if you take the topology generated by B, okay, tau B, that is contained inside tau D, because tau D is a topology after all. So what I want to show is that tau D is contained inside tau B, so that this itself is a basis for tau D. Okay, and this is a countable base. So that will end the proof. So, but this is one-line proof again. Let U belong to tau D and X belonging to U. What I have to do? I must produce a member from this B such that X belongs to that member and that member is contained inside U. So choose R positive first of all, such that BR of X is contained inside U. We are used to this one because every member of tau D is union of such members, where R is any positive number. But once R is positive, there is a n sufficiently large such that 1 by n is less than R by 2. Okay. Now, A is dense in X, I am going to use. So instead of arbitrary X, I am going to shift it to A. Okay, how A is dense in X? It follows that take 1 by n radius around X. This open ball, every open ball will intersect A. That is all, because A is a dense subset. So Bnx, B1 by nx intersection A is non-empty. Now take a point in this intersection. Then check that X itself belongs to B1 by nx, that is contained inside U. This part is obvious because X is inside this one, means distance between X and A is less than 1 by n, so it is symmetric. So this is here. But why this is contained inside you? Because I have chosen 1 by n as ln r by 2 triangle inequality over. The gist of this is that we are going to take this as a definition of having such an A which is countable in tens. This is going to be separability. And we are going to do that B1 by n's at each point, only countable thing. We are going to take the first countability. This gives you a big thing, namely, there's a countable base for the whole topology. There's a global base. So that gives you the third definition, which you are interested, which calls second countability. Okay. So we shall make a definition here. So we will now study these three notions in the reverse order. We say a topological space is second countable. Okay. Sometimes you just write double 2 here instead of second. Okay. If it has a countable base over. A topological space is said to be separable if there exists a countable dense subset over. Third one, we will wait for it. Let us make some, the third one was the first one which you started with there. Okay. Let us make some observations here. Typical examples of second countable spaces are Euclidean spaces. All that we have to do is consider the family of all balls with rational radius and centers at rational coordinates. When I say rational coordinates, all of them should be rational. Okay. So you can also see that finite product of second countable spaces is again second countable, because if you take a countable base, okay, countable base here, members from here to cross that one, they will give you base for the product. So countable cross countable is countable again. So finite products are countable. Every subspace of a second countable space is second countable. If you can generate all the members of the bigger space, okay, when you take subspace, look at, say, Y is a subspace of A, look at Y intersection members of B, where B is, so that will be a subbase for Y. Okay. So once again, this property is very important in analysis because it allows several countable processes, such as taking countable sums and integrations, etc. Because every open subset now will be union of from a countable family, right? So you can take U1 union U2, U1 union U2 union U3. So any union can be written as increasing union. So all these things are possible. Okay, so we shall first prove two easy consequences of this definition, namely second countability. Every second countable space is separable. That is why I took the other way around here. Okay, first I said second countable. The separability automatically comes here. So how? Start with a countable base for X. Okay. Let S be a subset of X which contains exactly 1 point from every member B of this curly B. One single point B inside B for each B inside curly b. The curly b is the countable base for x. Okay. Since I have chosen one point from each of them, this S will be again countable. This S is a subset of X, by the way. Okay. This is a countable set. Okay. Claim is it is dense. S bar is the whole of X. What is the meaning of that? Given any point X belonging to X and an open set U such that X belongs to U, there exists a B belonging to B such that X contained inside B contained inside U. Okay. But that means U intersection S is non-empty. Okay. So that B will have a point inside S, right? So B intersection S is itself is non-empty. So U intersection S is also non-empty. So what we have shown here is that it intersects every non-empty open subset, and that is the density. Every second countable space is another thing. It is Lindelof. Remember what is Lindelof? Every open cover has a countable subcover. This also is very easy. Why? How? Take an open cover. I must produce a countable subcover, right? Yes or no? So how do I do that? So UI is some open cover for X. But let us say B is a countable base for X because X is second countable. Okay. Consider all members of B which are contained in some member of UI. Okay. So that is a subfamily of B. Some of them may be too large. It must be some member of UI, that's all. So only take those things, call it B prime. Clearly B prime is countable because it's a subfamily of B. Okay. We claim that B prime itself is a cover for X. Automatically, this is subcover because we have taken only some families from these members UIs. Each of them is contained in some member of UI. So that will be automatically contained inside that. Okay. So all that I have to show is we claim that B prime is a cover for X. So let X belong to X be any. Take X belonging to UI for some I, because UIs are cover for X. Since B is a base, there will be some Bn such that X belongs to Bn and Bn is contained inside UI. This Bn is inside B prime by definition because I have taken those which are contained inside UI here. Therefore, X is contained inside only those B's which are inside B prime. Okay. Now, for each member B of B prime, choose one member UI which contains B. Okay. That forms a subfamily of UI which is clearly countable because I have chosen one for each Bn. And they are bigger subsets than original B, so they will cover X. Now I come to the first countability. Look at a topological space X. So I want to define another concept here, which I have not done so far, namely by a neighborhood system or a local base. There are two names for the same concept. Okay. Some people call local base, some call neighborhood system. For at a point X belonging to X, we mean a collection of open subsets UI of X such that X is inside UI for every I. Okay, so they are all neighborhoods. Secondly, given any neighborhood, namely some open subset such that X inside U, there exists a UI such that UI is contained inside. So this part is similar to base. Okay, but everything is happening at a single point x. That's why it's called local base. That is all. Okay. Away from x, this x is fixed. Away from x, this collection may not have that property. For only for neighborhoods of x, x belong to you, you will have a ui which is contained inside. So that's called a local base. Okay. Clearly, collection of all neighborhoods of a point forms a neighborhood system. You are very generous in taking all of them here, then it's no problem. But this system may be unnecessarily huge. And so we are looking at cases when there are neighborhood systems which may be countable. And that is the third definition for today. We say a space X is first countable at X belonging to X if it has a countable local base at X. If this happens at every point, then we will say X is first countable. Now, we said second countability implies separability, we have seen. Second countability implies first countability also. Because if we have a global base which is countable, a global base is always a local base also. Right? Therefore, second countability implies first countability. So out of these three, second countability is the strongest. Okay. Once again, a typical example of a first countable space is any metric space. No need to take Euclidean spaces. Of course, Euclidean spaces are first countable. Okay, that was our motivation. All that we have to do is take balls of radius 1 by n at each point. Point is fixed. Take all the balls of radius 1 by n. That will be a countable base, countable local base. Every second countable space is first countable. That I observed already. The converse need not be true. If that was the case, then we won't have two different definitions here. Okay. Easy counterexample is obtained by taking a discrete topology on an uncountable set. Okay. An uncountable discrete topology cannot have a countable base. Think about that. Whereas a discrete topology, each singleton is an open set. So I can just take that open set, namely singleton, as a local base. That's all. One single set will give you a base, local base. Okay. The importance of this local base, okay, is more or less due to the following fact. It allows us retain the notion of sequential continuity intact. Intact means what? Sequential continuity was true inside metric spaces. Now, first countable, it is coming from the metric space. That is what we have seen, the notion of that one. So only that is the key there, not the rest of the metric space structure. First countability is playing the role of this importance of sequential continuity. Let us see. Let X be a first countable topological space. Then any function f from x to y is continuous at x belonging to x if and only if xn inside x converges to x should imply fxn converges to fx. Okay? Proof is exactly same. One way is always possible. You don't need first countability. Okay, xn converges to x, f is continuous, fxn converges to fx. This is always true in any topological spaces. The converse, suppose for every sequence xn converging to x, fxn converges to fx, then how to show that f is continuous? The proof is exactly same as in the case of metric spaces. Okay, so let us go through that. I am trying to put converse here. Converse, assume that f is sequentially continuous at x and not continuous at x. Then you will get a contradiction. Okay, not continuous at x means what? There exists an open set U in Y such that fx belongs to U, but no open set V in X such that X belongs to V and f of V is contained inside U. Now I apply this part, no open set blah blah blah, to each of these basic elements here, Bn, local base. Okay. For each n, take an x1 inside B1 such that f of x1 is outside U. After that, you take B1 intersection B2, that is an open subset containing X. So take X2 inside B1 intersection B2. It may be X1, don't worry. Okay, take Xn in the intersection of B1, B2, Bn inductively, such that f of xn is outside U. Okay, automatically this implies xn converges to x. Okay, but fxn doesn't, it is very poor, it is far away outside U, so if fxn cannot converge to fx. So this contradiction proves the claim. So I have a few exercises here and a comment. Show that every subspace of a first countable space is first countable, second countable space is second countable. This I have already explained. Same explanation is there for one also. As an exercise, you write down the details. In particular, deduce that a discrete subset of a second countable space, okay, has to be countable. This is used in complex analysis. I don't know whether you have done this kind of things. The set of zeros of an analytic function is defined on a domain of C, right? On open and connected subset of C. It may be the whole of C. It will be automatically countable. So how do we prove that? By proving that it is discrete. Automatically it will be countable. Show that if F is a family of closed intervals of positive length which cover the whole of X, there is a countable subfamily of H which covers R. X is R here. If it is open intervals which cover R, countable family will cover because it's Lindelof. Okay, we have proved that R is second countable, and second countability implies Lindelof, right? So open intervals covering the whole of R will have a countable subfamily covering R. But I want it closed intervals. Closed intervals, you don't take single points. No single points are allowed. Okay, intervals will be of positive length, that's all. A, B, closed interval, A less than B. Take such things, then you will get a countable subfamily which covers it all. So this you have to do is only R. This is some tricky thing. On an uncountable set X, let tau be the cofinite topology. Okay, this is our favorite example. Is X tau with cofinite topology here first countable? Is it second countable? Is it separable? Check them, because you check these things, you will understand these concepts properly. Okay. So that's all for today. Thank you.